Tava entrando.
Pronto. Então tá entregue ela
Tava
pra
no
ele.
buraco errado.
Testa aí.
Me disseram que ela foi vista com outro num fuscão preto pela cidade
Tem delay mesmo.
ruda.
O quê?
Chegou agora.
Okay, we can start. So let's start with just explaining yesterday's problems. We'll pick out the statements here. Alright, problem A was probably the easiest, as it usually is, to introduce people to the contest. So we have some array A1, A2, A3 to AN, and we should find the first index I such that AI plus 1 etc through AN form an arithmetic sequence. So there is an integer d such that an minus 1 equals the an minus 1 minus an minus 2 equals etc. Each pair of two consecutive elements, when we subtract this element from this element, we get the, when we subtract this element from the next element, we get the etc. And the first thing to notice in this is that the difference d is already given uniquely as the last element minus the second to last element. The rest, all we need to do is check if, when we know this d, if this holds for the second to last and first to last element. So an minus 1 minus an minus 2 is equal to the an minus 3 minus an minus 4 is equal to the etc. And at some point, if we find out that some ak minus ak minus 1 is not equal to d, then the first element of that arithmetic sequence we wanted is k. Obviously k is at most n minus 1. This is all we need to do. It's quite simple. And of course, this works in linear time, in the size of the input. Probably the second easiest problem would be forest picture, which is just about drawing a picture and then finding the smallest bounding box. So we are given some positions of trees that are drawn on a picture, trees and stumps. A stump is basically a tree with height 0, ASCII characters, and a tree is something that looks like this. It should be. since the trees and the stumps are all the trees and all the stumps are non-intersecting with each other, then there are no questions about which character to use if we have some intersecting ones, fortunately. And all of these trees and stumps are with fixed coordinates of the bottom. We can just make an array of m by m characters. The resulting image should have size m by m, where if some trees or stumps have characters that go outside of that m by m image, just should discard them and shouldn't print them. And that's basically it. This is the kind of annoying problem that sometimes appears in low-level contests, where you just have to correctly parse the input and correctly print the output, and there is basically no ideas, no programming in there. When I was competing in one of those CTU contests a few years ago, there was one problem that also was a lot about printing the output in the correct way. And there were no provided inputs and outputs in text form. There weren't any files that show exactly how the input and output should look, but we only had PDFs. And in the PDFs there were characters in the output that were basically quotation marks, like this. And maybe you know that there are a lot of different ways to print characters. There is ASCII, Unicode, etc. ASCII has 1 byte representing each character. Unicode has more. And these characters that were in the PDF were Unicode. It didn't make sense at all, and I copied them into a text file and then tried to read them, because I was always getting some errors and it was weird. What I should have done was just write, not copy it, but write the input into a text file as I saw it in the PDF, which is when I would have written this standard quotation mark single quote, which is an ASCII character. So shit happens. I spent a lot of time on that, maybe an hour in the contest, because I just couldn't understand why this just didn't work. That's why contests should provide always some in text form, or just make it available on their website to download in text form. The next easy problem would be chessboard dancing, or when we remove the part about dancing, because it's completely unnecessary here. It's just flavor text. Then it would be that we have a chessboard with size some s times s squares, for example 6 times. And in each square of this chessboard there is either one knight or one bishop or one rook or one king. When there is one knight in this square, when there is that one knight in each square, then this knight attacks, the knight from this square attacks this, and this at most 8 squares, where each of one coordinate of the difference between the knight square and the attack square is 2 in absolute value, and the other coordinate is 1 in absolute value. And we should split those pieces into teams, where if one piece attacks another piece, then these 2 pieces should be in different teams. So for example, the knight that's in this square has to be in a different team than the knight in this square. It doesn't really matter in what way we split them into teams, but the number of teams should be minimum possible. And it's basically 4 problems in one, because there are 4 things that you need to handle completely independently of each other. But they are all quite simple. For example, for the knight case, we can cover the as they are in a typical chessboard. And as you can see, when I've covered each alternating diagonal black and left the diagonals between them white, then you can see that the knight from a white square will always attack black squares, and a knight from a black square will always attack just white squares. And so it's enough to put all knights from black squares into the same team, and all knights from white squares into the other team. And we only need 2 teams. There are of course some special cases to handle. With knights there is the 2x2 chessboard and 1x1 chessboard, if they appear in the test data, which is when we can just put all 4 or that one piece into one team. So here we would have team 1, 2, 1, 2, 1, 2, 2, 1, 2, 1. 2, 1, 2, 1, etc. Here we would have just 1, 1, 1, 1, and here we also would have just 1. Then there is the case with rooks and the case with bishops, which are very similar. Because with rooks, when we have when we take just one column of the chessboard, then we can see that all rooks in that column will attack each other, so they all have to be in different teams. So we need at least S teams for rooks. So for this case, where S is equal to 6, then the teams can be split like this. And then it can be shown that these are sufficient. Because we can do the same for the first row, just like for the first column. And then for each diagonal, we can put all the rooks on the diagonal in the same team. For the first n diagonals, this is clear because we already know in which teams these rooks will be. The team for each diagonal, it's uniquely given by the way we chose the first column or the first row. But when we go to the next diagonal, it's not clear so far, but we can still just take the number from 1 to s that doesn't appear in the second row and put it in this square. So the rook from this square will be in the last remaining team out of the s that wasn't here. And then we can again just fill that diagonal, put all the rooks on the same diagonal. Then we can continue in the same way in this square, where we have 2 was the last missing number in here, since we filled that one for this diagonal. And we can again just fill this diagonal, fill this number, which is 3, fill this diagonal with 3, this number will be 4, fill this diagonal with 4, and the last number here left will be 5. So this ordering of the teams, this assignment of the teams will be sufficient to make just S teams if the chessboard is S times S. And basically the same thing works for bishops. Again, we can just take the main diagonal or the dark square diagonal of the chessboard. And we can see that all the bishops that are on this diagonal will attack each other, because 2 bishops attack each other if they are on the same diagonal, either like this or like this. And therefore we can again see that we need at least S teams, and we can make those S teams even easier than before. The first row will have team 1, the second row will have team 2, etc. Each row will have all bishops in the same team according to the number of their row. And then it's clear that if 2 bishops are in squares where they attack each other, then they are on the same diagonal, but they are in different rows, so they have different teams. There are no special cases to handle here, so we have knight at most 2, rook at most, rook exactly S, bishop exactly S, and the last remaining case is the king, which is where if we have a king in some square, then this king will attack all 8 squares that are surrounding it, or up to 8 if it's on the border. A king attacks these 8 squares, and let's focus on just 4 of those squares that it will definitely attack if the chessboard has size at least 2 times 2. Of course, if it has size 1 times 1, then the answer is also at most 1. So if we have 4 squares in a 2x2 sub-chessboard where each square contains a king, then each 2 of these kings attack each other. So these must all be in different teams, and we need at least 4 teams. Of course, it's easy to see that we need at most 4 teams, because we can just take the first row of the chessboard and assign the kings in that row to alternating teams, just like in the knight case. This will be team 3, this will be team 4, and then what team should this king have? 1, 2, 4 are in this 2x2 square, so the king should again have team 3. This king should have team 4 for the same reason, team 3, team 4, etc. And for the next row is the same as for the first row, 1, 2, 1, 2, 1, 2. The 4th row should be the same. As the second row, and so on. And we can see that if we have a king in some square, then all the neighboring squares, all the squares it attacks, have kings that are in different teams. The ones that are in one team, the 2 that are horizontally adjacent are in one team, and the 2 that are vertically adjacent are also in one team. So in total we really only need 4 teams if the chessboard has size at least 2, and 1 team if the chessboard has size 1. So for the king the answer is at most 2. You didn't actually need to find these arrangements, just compute. Just find these numbers that for the knight it's 1 or 2, for the rook and the bishop it's S, and for the king is at most 4. These were the trivial problems. Well, there is one more, but I will keep it for a little bit later. Then there are the kind of easy problems that use standard algorithms. Shooting gallery is a very standard dynamic programming. The problem statement was that we have a sequence of ducks put in a row. There is this saying in English, don't put all your ducks in a row. And maybe this problem statement was taken from it. I'm not sure. So we have ducks, and each of those n ducks is of some species. The species of the ice duck is AI, and there is some shooter that plays a game. The shooter must choose 2 ducks that are of the same species. So for example, if A2 and A10 are of the same species, then the shooter can choose this, shoot them, and then what happens is that these 2 ducks are removed, and all the ducks that are to the left of this duck, of the duck with the smaller index, are removed. All the ducks that are to the right of the duck of the short duck with the higher index are removed, and the shooter can continue playing the game on only those stacks that were between the two that he just shot. If there is no way to choose two decks that are of the same species, then the game is over. And the point of the game is to shoot in as many rounds as possible. So it's quite obvious that if the shooter chooses some indices I1 and J1 in the first round, I2 and J2 in the second round, I third round, etc. IK and JK in the K round, so the shooter shoots in a K round, if it's possible for the answer to be K. Then we need to have I1 at most J1, then I2 and J2 are shot only from the decks between I1 plus 1 and J minus 1, so I1 is greater than I2 is greater than J2, and also J2 must be smaller than I2 sorry, J1. The same thing holds for J3, so I1, I2, I3, J3, J2, J1 must be the order of these indices, and so on up to IK and JK, where we need to have the order of indices I1, I2, I3 up to IK, and then JK, JK minus 1 up to J2, J1. This must be for the deck with this index and this index, they need to have the same species. So AI1 is the same as AJ1, AI2 is the same as AJ2, etc. And this is basically the definition of a palindrome. So we just need to find the longest palindromic subsequence in the original sequence, where the subsequence doesn't need to be contiguous. We just we can skip some decks in between the shot ones. And this is a well-known problem that's solved with dynamic programming. Where we can just count number of rounds that can be played if we are left with decks L through R, so AL plus 1 up to AR. Obviously, this is, we can just discard the first deck, or discard the last deck, or maybe shoot these two. So if AL is equal to AR, then we can shoot deck L and deck R, and this number of rounds is I'll just write it with LR. The DP number for this position is the same as the DP number for position L plus 1, R minus 1 plus 1, because we just shot that pair. If we can shoot this pair of leftmost deck, rightmost deck, then there is no point in not shooting it, because we would still have to discard one of those decks, and there wouldn't be any point to it. But if AL doesn't equal AR, then we can either discard the leftmost deck or discard the rightmost deck. So the number of rounds for this state is the number of rounds for state L plus 1R, which is when the leftmost deck is discarded, and L R minus 1 which is when the rightmost duck is discarded. This is the very standard DP solution. The next one of the easy problems would be go northwest, which after the long statement is parsed just reduces to this problem statement that we have some points marked on a map. Each point is at integer coordinates xy, so x1, y1, x2, y2 up to xn, yn, and the game goes as follows: that we choose two of these points, and if they are on the same diagonal, either on the same 45 degrees tilted diagonal like this or like this, then the game is won by the first player, otherwise the game is won by the second player, and we want to know the probability that the first player wins the game, or something like that. Since probability is the number of cases where there are the number of pairs of points such that they are on the same diagonal, so the number of success cases divided by the total number of cases that could happen in this game, so this is just the number of pairs. The number of possible pairs that could be chosen is always n times by 2, because we can choose 1 point. There are n ways to do this, then we can choose the second point. There are n minus 1 ways to do this, since we can choose the first again, and the number of the each pair that we could choose like this is counted twice, either by choosing this point first and this point second, or by choosing this point first and this point second, so we divide it by 2.
Actually, I think in this problem we could use the same point for the first coordinate, and I mean there are two people, right?
Yeah.
Choosing cities. They can choose the same city, so I think it's n squared. I remember implementing. I think it's n squared.
Each one has a pole with the cities,
Yeah.
and they are separate poles.
You can choose equal.
The first sentence of the fifth paragraph says that both towns can be the same.
And the order matters.
Oh, right. I mixed it up with the second part. Yeah. So, right, it was like this, that each player has those endpoints, and one player chooses 1 point independently, the other player also chooses 1 point independently, and if they are on a diagonal like this, then one player wins the game, and if they are on a diagonal like this, then the other player wins the game, otherwise the game ends in a draw. Like, it was like this. and we just want to find out what's the probability that the game won't end in a draw, but is the same if we wanted to find the probability that the first player wins or that the second player wins. It can all be found in the same way. So there is a winner if both those points are on the same diagonal and if they are on the same points. So the number of pairs is n times n, since each player chooses independently, and the number of pairs can be found by either imagining the problem rotated by 45 degrees and then counting the number of pairs on each row or each column, because if we shift like this by 45 degrees, then this diagonal becomes a row and this diagonal becomes a column. Or we can just group the pairs, group the towns or the points by the diagonal on which they appear, or either in this direction for these diagonals or for these diagonals. And for both of those cases, for both types of diagonals, just count for each diagonal how many points appear on it, how many pairs of points appear on it. The number of pairs that appear on a diagonal with k points will be k times k minus 1 divided by 2 for the reasons I just explained. So this number of pairs that are on the same diagonal is the sum over all diagonals of k minus 1 divided by 2, where k is the number of pairs on this diagonal, and this sum is taken over both these diagonals and these. The diagonal, this diagonal, the points appear on is given by, if this is the y coordinate and this is the x coordinate, and this is a point xy, then all the points on this diagonal will have y minus x equal to some constant, the same for all those points. So we can just put all those points in a map depending on their value of y coordinate minus x coordinate, and then loop over all those entries in a map, and we have for each diagonal the number of points that appear on it. Diagonal, just the points that appear on it have y plus x the same.
Then in this case the order matters, so we can divide by 2. The sum of the pairs.
Yeah.
The order matters, but it's the order kind of matters because it's just a constant of 2, but we are only looking for the winner, so it's whatever. This is the with not dividing by 2 is the probability that one player will win, and if we divide by 2 is the probability that one specific player will win. Then we have problem ice cream samples, which is about some ice cream stands in a circle. And for each ice cream stand we have some group of ice cream types that are sold in this stand, and we want to just start at some stand, buy all the ice cream types that are in this stand, then move on to the next stand in the circle, buy everything buy those ice cream types that are in this stand. Of course, in each stand can sell more than one of each ice cream type. There's no reason why it wouldn't in this problem. And we go on to the next stand, up until the point where we find out that the number that for each of the K types of ice creams, we bought at least one sample. And we want to minimize the total number of samples we bought, since, of course, some ice cream types for some ice cream types we could have bought more than one sample. This what I just described would be trivial in O n squared, because we would just simulate for each starting point how we would go. Okay, it would be n times number of ice cream types that are sold in all those stands. And we can do better. One way is to just try binary searching for the answer for the minimum total number of ice cream types, and then for each starting stand we know up to which finishing stand we can go based on the sum of numbers of samples that are sold in each stand. And then we just would have to check if there is enough, if each type of sample is bought in one of those stands. But we can also make a faster solution, because that would be something like n log n. And the faster solution is to try a two-pointers approach. First of all, we will discard the circle and use problems where we just write those ice cream stands if they are numbered like this. Then we would just write them in a row. One through n, and then again 1 through n. And now, instead of going in a circle and, for example, looping over, which would be kind of complicated to implement, we can just say that we start at some point in this array, which is all those stands repeated twice. Start at some point and go up to some other point. So, for example, if we started at 4 and went to 5, 6, 7, 1, 2, 3 again, then it would correspond to this. Of course, there is no point in going over n stands. In some problems, we need to watch out not to do it, not to consider going from some stand to more than n stands farther. But in this case, it doesn't matter, because it wouldn't gain us anything. There wouldn't be any more types of ice creams, and the number of ice creams in total that would be bought would just increase. And what we do on this array is a two-pointer algorithm, where we start at 1, find out how far we have to go at least to get the ice cream of each type, just by counting the number of types of each ice cream that were bought so far. In general, we could use a map, but in this case, since k is sufficiently small, we can just use a simple array. So we can just we start with one pointer here and move the second pointer further until we find, for example, that we only need to go up to stand 4. And we also count how many ice creams we must have bought between the stand marked by the first pointer and the stand marked by the second pointer. Then we move on to the second stand, subtract all those ice cream tiles that were in the first stand from that array of numbers of ice creams bought so far. This pointer is moved here, and then we have to move this pointer further. Of course, it can't decrease, so we only move it in total n times. So we move the next pointer further up till we again find out that the number of for each type of ice cream we bought at least one ice cream of this type, and so on. We move this pointer. We again move this pointer, etc. Of course, the second pointer can just go up to the two-nth object in this array. We don't loop over again. And that's basically it. We just found out for each starting point how far we have to go and how many ice creams we have to buy, and we just choose the minimum of these numbers of ice creams. Now we are getting to some slightly harder problems. There was pond cascade, which is about again an array of pond in a row. So we have a pond with capacity A1, then a point with capacity A2, etc. up to an minus 1 an, and I'll draw arrows between them, because what happens is that we start pouring water into each pond at a flow rate of some f per second or f per unit time. This f is the same for all ponds. And what happens if we fill each pond with water to its capacity is that the water from this pond starts overflowing to the next pond, again with flow rate f. If we fill both of these two ponds with water, then the water from this pond will overflow here, but the water from this pond will overflow here. And since we have f units of water flowing here and f units of water flowing to the same point from the valve that went directly to that pond, then we have 2f units of water flowing to the next pond, etc. And of course, it can happen that, for example, pond 2 has a very large capacity. So at first we have just f units of water flowing. Pond A1 has a very large capacity, so we have f units of water flowing from pond 2 to pond 3 if pond A2 overflows. And then when A1 starts overflowing, then this number will increase to 2f, and so on. So this is a quite complex process where we don't know the order in which the ponds will start overflowing, because the amount of water that flows into some pond can suddenly increase by f. Of course, it's possible to simulate this with some priority queue and a somewhat complicated approach. But why would we do this if there is a simpler approach, which is binary search? Right, what we want to find out is the time when the last pond starts overflowing and the time when all the ponds start overflowing. Of course, if the last pond starts overflowing, then the water from it will just flow into a drain somewhere away. Doesn't matter at which rate. And we can binary search each of these times. If we have decided that we want to find out what are the states of all the ponds at some time f, some time t, then we know that we had f times t water that flowed into pond A1, and if f times t is smaller than A1, then pond A1 isn't filled completely and we can just continue, it doesn't matter. We can just discard pond A1. But if f times t is at least A1 or greater to A1, it doesn't matter, it's the same case. For equality, then we have f times t minus A1 water that flowed from pond A1 to pond A2 plus f times t amount of water that flowed through the wall directly to pond A2. And this can be either smaller than A2 or greater or equal to A2. If this is smaller than A2, then we know that even though some water flowed from pond 1 to pond 2, then pond 2 didn't overflow. And continue. And if this is greater or equal to A2, then we know that the remaining amount of water, which is f times t minus A1, 2f times t minus A1 minus A2, flowed into pond A3. And we can do the same thing with pond 3. That say that f times t from the direct wall plus f times t times 2 minus A1 flowed into it, and continue checking if this is smaller or greater than A3, and so on. And like this, we know whether all ponds overflowed, which is sufficient for deciding if all ponds overflowed at least at time t. And when we reach pond AN, then we also know if pond AN overflowed, so this is sufficient for checking if this time is greater or equal, if time t is greater or equal to the time when pond N overflowed. There should be 3 problems left. Another standard problem is punching power, which is that again we have some points on a plane. Each point is at integer coordinates, and we want to choose as many points as possible from these points with the condition that none of these two can be at a distance smaller than 1.3. 1.3 looks like somewhat a random number because it's just a fraction, but since the points are at integer coordinates, then if we have 2 points with positions x, y, and for example x, y plus 1, then these two will have distance 1, which is smaller than 1.3. But if we have 2 points such that they differ by at least 1 in each coordinate, so for example x minus 1, y minus 1, then the distance between these 2 points is the square root. Of course, it isn't directly mentioned that the distance is Euclidean distance, but it should be expected if there is nothing mentioned about what kind of distance. Square root of x coordinate squared plus y coordinate squared, which in this case is square root of 2. And square root of 2 is approximately 1.4, which is greater than 1.3. So that 1.3 just says that the points have to have a distance at least the square root of 2. And so that the points need to be non-adjacent. This is why I called it a very standard problem, is that the points, finding some points that such that none of them, no pair of two chosen points satisfies some special rule, is basically matching in a general graph where the rule describes edges in that graph, and we need to find an independent set. Okay, independent sets and matchings aren't the same in general graphs, so it describes finding an independent set or vertex cover, since independent sets and vertex covers are the same in any graphs. The problem is that matching can be found in polynomial time in general graphs using Edmonds' boson algorithm. Also something that you shouldn't remember, but just should be able to copy. So I'll write the concepts here: independent set, vertex cover, and in general these two are the same. And then we have matching, which is not the same. And then we have bipartite graphs, here matching is Edmonds' algorithm in O and don't know, n to the power of 3 or n to the power of 2 or something. O polynomial in a number of vertices and number. And this is exponential apparently so far. And then we have bipartite graphs for which matching is the same as independent set and vertex cover, according to Koenig's theorem, I think. And it can all be found using some various matching algorithms, flow algorithms, these things. In bipartite graphs it's easy to find matching as using reductions to minimum cool maximum flow. So the simplest of these algorithms would be Ford-Fulkerson, which runs in O and M. Of course, M can be up to n squared, but in this case we'll see that the graph is bipartite and M is sufficiently small, so it will be basically O n squared. O n squared in total instead of O n to the power of 3. And there are some fast algorithms that are much more complicated, and the running time in this case would be something like n square root of n. But I'm not going to explain this, just this. And find out why the graph is bipartite. So we have these points, and we know that each pair of points that are adjacent, that have just one coordinate difference equal to 1, and the other coordinate is equal. So xy and xy plus 1 cannot be chosen at the same time. So there will be an edge between them in that graph. But just like we painted the chessboard in the problem with chessboard dancing in the part with the knight, we can take all those points in a plane and color them like this. So we have black points on diagonals and white points on diagonals. And now we can see that this graph, in this graph we have edges between all adjacent pairs. But there are no edges between 2 points of the same color. There is no edge between 2 white points or 2 black points. So the white points for one partition of the bipartite graph and the black points for the other partition of the graph. Of course, there could be a lot of points if we just made the whole grid like this, since the coordinates are up to 10 power 9. But we can just check all pairs of points, and if they have distance 1, then add an edge between them in the resultant graph, and just take all points that have, for example, sum of x and y coordinate even to one partition and sum of x and y coordinates odd to the other partition. And then we need to find out what is the maximum matching in the resulting graph. So we have partition of black edges, partition of white edges, for example, like this, and we have some between them. And of course, since each edge can only be between 2 adjacent points, and each point only has 4 adjacent points, then the maximum number of edges from any point, from any vertex in this bipartite graph is up to 4. So M is really up to 4n, where n is the number of vertices in this graph. What we do for finding the maximum matching using Ford-Fulkerson is Ford-Fulkerson is a flow algorithm, and what we do is that we add a source and a sink, connect all the vertices from one partition to the source, connect all the vertices from the other partition to the sink, and all edges here have capacity 1. All edges have capacity infinity, and all edges here also have capacity 1. And we want to find the flow in this graph because hold on, these have also capacity 1. since the edges have only capacities 1, then if we have some flow through one edge, then next edge here. So from the source to the sink, we can always have only one unit of flow flowing to one black vertex, then from this black vertex to a white vertex, and from the white vertex to the sink. This unit of flow goes through one edge, and it's clear that since there is the edges are direct direction, then since each black vertex has the capacity of incoming edges equal to 1, and each white vertex has capacity of outcoming edges equal to 1 also, then we can only have such that there is there is a flow out of this vertex through that edge, and only one edge such that there is a flow through that edge to this vertex, which is basically just matching those vertices using edges for which we have a flow going through these edges. And it turns out in fourth Fulkerson algorithm that all we need to do to find the maximum flow is to just add for each edge that goes from left to right with capacity 1, one edge that goes from right to left with current with also capacity 1, with capacity that can change depending on what's the flow through this edge, that there is a pair of edges, and if there is a flow of 1 through this edge, then this edge has capacity 1, and we can do something like this, that we decide to send a flow of 1 back through this edge and stop sending a flow of 1 through this edge forward. So if we would have a flow through this edge, you will have a flow through these edges from the source to the sink. Then this edge would have capacity 1, and this would have remaining capacity 0. And what we are doing is that we just run a DFS or BFS through that graph and find a path from the source to the sink that goes only through edges with capacity 1. And we use these edges to replicate some case where we decide that we don't want to forward, but just want to redirect it, not send it like this, but send the flow that went here, for example, through this edge. If we decided to do this, we would just say that this edge has capacity 0, this edge has capacity 1, remove the flow that went through this edge, send it through this edge, and say that the backwards edge that went from here will have capacity 1 now, and this edge will have capacity 0. So we always have, instead of one directed edge that goes that goes from the left to the right, we would have 2 edges where one goes from the left to the right and the other from the right to the left. initially the one that goes from left to right has capacity 1, and the other has capacity 0. And if we want to send the flow in the other direction, or just, well, if we want to send the flow from left to right, set this edge to capacity 0 and this other one to capacity 1. And if we want to cancel it, then we reverse it. So they always have sum of capacities equal to 1. And if we have this, we could use these resulting capacities to reconstruct the optimal matching, but it's often not so simple. I won't describe it here because it's a topic for another day, but it's also interesting and sometimes complicated. What we are doing in the fourth Fulkerson algorithm, so as I mentioned, we always just find an edge, a path through edges with capacity at least 1, and it goes from the source to the sink, and then we send a flow through that path. Of course, the path can use these backwards edges. There is no reason why it shouldn't. That's why these edges are here. So, for example, we could use a path like this, send a flow through it, flip those capacities, and add a flow of 1. Because we always, even though we redirected the flow, then the flow we sent through from the source to some edge is always increased by 1. It turns out that when at the point where we can't do this, we have actually found the maximum flow. So the number of repetitions of that algorithm is equal to the maximum flow, therefore to the maximum matching. And since we have some vertices that were matched, and each vertices that were matched have to be in such that only one of them can be chosen. There can't be any other pair of vertices such that they can be chosen at the same time and they haven't been matched, because if there were, then we would run this fourth Fulkerson algorithm using one more iteration, and the maximum flow would increase. And the total number, the size of the independent set is the number of vertices minus the size of the matching. So if we found the size of the maximum flow, then we know the size of the matching, which is the same, and the number of vertices in the largest independent set, which is n minus the size of the matching, I think. This is ONM because we run at most n iterations. The maximum flow is at most n because there are only up to n edges from the source and up to n edges to the sink. And in each iteration we run an ON plus M algorithm. Okay, this is technically ON times n plus m, an n plus m algorithm like BFS or DFS. And it's actually interesting that BFS is slow here, and DFS, or cleverly done DFS, can be much faster. That this problem has had a constraint of n up to 2000, so this would be some 4 million n times m, or several tens of millions. If there are many edges, if there are about 4n edges, but we could easily have n up to, I don't know, 10,000, maybe more, and with a properly done fourth Fulkerson, with this complicated techniques or whoever's algorithms that run in a faster time. I've already done that in some contests that I wrote for Fulkerson using BFS and it was too slow, so I rewrote it to DFS, optimized it a bit, not to use the same edges, not to look at the same edges with capacity 0 too often, and it completely destroyed the needs. Completely destroyed this faster solution. Because you can notice that quite often the size of the paths that we need to take is just about 3, 1 to 3 edges. So we can say that there are a lot of iterations in which if we look at the right vertices, then we only needed some constant number of looking at the next vertex and the next edges. And in some other iterations, it's okay, we could have spent some more time. But if there are very few of these iterations, then it doesn't matter if we spend O(n)m time in each of them. O(n) plus m time in each of them. Alright, I spent a lot of time on this problem, so let's take a break again. For example, up to 10:15. Right, I meant 11:15, not 10:15.